Hi to all. Today's topic is mutual inductance between two coaxial solenoids. For example, this is a block color one. It's a solenoid with a number of turns N1 and area of cross section A1 and the current through it is I1. There is another solenoid is there that is in the blue color line. Its number of turns N2 and the current I2 and area of cross section is A2. Right? There are these two solenoids are coaxial solenoids. One is inner solenoid and other is outer solenoid. Inner solenoid has the number of turns N1, current I1, area A1. Outer solenoid number of turns N2, current I2 and area A2. I am considering that these two are very closely wound one over another, then these are the tightly packed. The area of cross sections are nearly equal. Okay. Now let us see here. I am going to derive the formula for mutual inductance between two coaxial solenoids. In this, what happens when the current changes in the inner coil, the newly current induces in the outer coil. That is the mutual induction. When current changes in the outer coil and then the current induces newly in the inner coil, that is also called as mutual induction. And now mutual induction is nothing but induction of current in one coil. In one coil, current generates due to the change in another coil, another neighboring coil. Due to the change in current in neighboring coil. Now let us see here. The magnetic flux link with the outer coil I want or the inner coil I want. Magnetic flux link with N1 turns of inner coil. N1 turns of inner coil. That formula is N1 phi1. Okay, N1 phi1 is equal to M12 into I2. Actually, what happens? The flux link with the inner coil depends upon the current in the outer coil. The flux link with the first coil depends upon the current in the second coil. By that we got one equation, that is the flux link with the first coil is N1 phi1. That is depends upon the current in the second coil, outer coil, that is I2. When we remove the proportionality, we will get a constant that is M12. We know already that is the mutual inductance in the first coil due to second coil. Now let us see, this we can consider as equation 1, and in this phi1 is the flux link with the Phi1 is the flux link with the first coil, inner coil. First means inner coil here. Okay, right. Then here we write, but this we can take as equation 1. In this, Phi1 is the flux link with each turn of inner coil. Flux link with each turn of inner coil. Each turn means only one turn. Inner coil. Okay, let us start. What is this phi1? The phi1 is equal, we will get as magnetic induction into area. Actually, the flux link with the inner coil due to the field of outer coil. We write the B2 A1 cos theta. For example, here we are considering that the areas of two coils are nearly equal. That we can take as capital A. Here B2 A1 cos theta. The field due to outer coil is right side and area vector also right side. We take theta as 0, then we write as B2 A1. Okay, A we take. Here we are taking that A1 as A and theta as 0. When you substitute these two conditions, then here we will get B2A cos 0. Cos 0 is 1. Then finally we will get the flux link is B2A. B2A. Okay, this we substituted in equation 1. Equation 2 substitute in equation 1. Then what you will get? That is N1 into phi2 is B2A. Right? This is equal to M12 into I2. But one thing, what is B2? B2 is the magnetic induction, but magnetic induction B2 formula is, B2 is the magnetic induction due to outer coil. That formula is mu naught. For example, this is the outer coil, number of turns per unit length is N2 and current is I2, then we write mu naught Ni2. Okay, this we substitute in this equation, then we will get N1 mu naught N2 I2 into A is equal to M12 into I2. This I2 will get cancelled, right? This one and this one will cancel. Then finally we will get like this, that is M12 is equal to mu naught capital N1 into N2 A, right? And here we write the capital N1. What is capital N1? We write in terms of small n1. I want to write. We know the small n1 is capital N1 by L. From this, capital N1 is equal to, we write as N1 into L. And this equation will become like this, that is M12 is equal to mu naught capital N1 we write as N1 into L, N1 into L into N2A. Then finally mutual inductance in the first coil due to second coil we will get as mu naught N1 N2AL. This is the equation, and this is the important equation we derived at here. This is equation 3. Okay, right. And the next one here, what we derived, when the current passes through outer coil, the magnetic flux link with the inner coil depends upon the current in the outer coil. When current in the outer coil changes, flux link with the inner coil changes. When the flux link with the inner coil changes, EMF induces in the inner coil. That is called as mutual induction, and it is a formula for the mutual inductance. Now I am going to derive the same format for the, for example, if the current changes in the inner coil, right, then flux link with the outer coil changes. When the current changes in the inner coil, this inner coil, the field generated by the inner coil changes, flux generated by the inner coil changes. The flux generated by the inner coil link with the outer coil, due to that the current induces in the outer coil. That is also mutual induction. That means induction of current in outer coil due to change in current in the inner coil. Let us see here the flux link with the N2 turns of outer coil. Magnetic flux link with the N2 turns of this length we can take as L, length of each solenoid. Magnetic flux link with the N2 turns of outer coil. Right, the flux link with the N2 turns of outer coil N2 phi 2. This will depends upon the current in the inner coil in the mutual induction, right? That is M21 into I1 we have to write. Okay, just if you know these all things, this derivation if you know, just we have to change 1s to 2s and 2s to 1, then you will write the same equations and you will get the M21 formula, right? Then let us see here, phi 2 is what? But phi 2 is equal, we write as phi 2 is equal flux link with each turn of outer coil. That is due to the field of inner coil. B1 A2 cos theta we have to write, but this is the B1 A2 only, because of theta is A2 is A and theta is 0. These two conditions we substituted here. That is A2A and B theta is 0. Then we will get cos 0 like this. And the flux link with we will get as phi 2 is equal to B1A we will get. This is equation 4 and this is equation 5. Now equation 5 substituted in the equation 4. The same method we have to do, right, and we have to derive the M21. There is a mutual induction in the second coil due to the first coil. Okay, and note every point and take the screenshot, and I will continue after the rubbing this. Now equation 5 substituted in equation 4. Equation 5 is substituted in equation 4. Then N2 phi 2 we write as B1A is equal to N2 phi 2 we wrote here B1A is equal to M21 into I1. Okay, right. Then here, but B1 is what? But the B1 is the magnetic induction due to first coil. This is depends upon the number of turns per unit length in the first coil, right? N1 and the current in the first coil, nu naught N1 I1. This is substitute in above equation. Then we will get N2 into B1 is mu naught N1 I1 into A is equal M21 I1. Now here we have to cancel the I1 at here. This is the I1 and I1 will cancel. And finally we will get the M21 formula, right? Mu naught N1 into N2 into A is equal to M21. Okay. And then here we have to change the N2 into number of turns per total number of turns in the outer coil. N2. Okay. Small N2 is the number of turns per unit length. That is total number of turns by total length. From this, if you write the N2, we write as small n2 into L. Okay, this we substitute in above equation. Then we will get to mu naught into N1. N2 we write as small n2 into L is into A, that is M21. Here, this we can change. What I did it here, N2 is replaced with small n2 into L. Small n means number of turns, total number of turns by length. Then finally we will get to M21 formula as mu naught N1 N2 AL. Okay, right. This is the mutual inductance in the second coil due to first coil. This is equation 4. As it is how we derived the equation 3, like that we have to derive, but in place of first coil, second coil will be there. In place of second, first will be there, right? And from equation 3 and 4. From equation 3 and equation 4. No. This is equation 3. Equation 4, 5 completed, and this is a 6. Equation 3 and equation 6. What we write? The mutual inductance in the second coil due to first coil, or the mutual inductance in the first coil due to second coil is the same. That is the mu naught N1 N2 AL. And this we can simply we write M is equal to mu naught N1 N2 AL we write. This is the mutual inductance between the two coaxial solenoids. This is equation 7. In this, capital M is called as mutual inductance between two coaxial solenoids. Capital M is the mutual inductance. Okay, right. In this, if you want to change the small n1, small n2 into capital N1 and capital N2, then what we will get? Okay, but we know what that is. Small n1 as, I will write in the right side. I am going to write the right side and take the every point. Alright, what I am going to write here, but we know number of turns per unit length. N1 is equal to we know as N1 by L, and N2 is equal to we know as N2 by L. Okay, right. Then this you substitute in above equation. Okay, from equation 3 we will get as mu naught N1 we write as N1 by L into N2 by L into AL we write. This we write as like this, that is mu naught N1 N2 A by L. Okay, this is also mutual inductance between the two coaxial solenoids, right? This is equation 8. And the next one important point I will explain in the note, right? That is, if the coils have different areas, okay, I am going to give some point that is in the note, right? If the two coaxial solenoids have different areas, then what you have to take, which area we have to consider? We derived the case that where the area of cross sections are nearly equal. But if the, okay, let us see here one point that is in the note I am going to give. If the solenoids have the different areas, okay, right. In this case here the solenoids have the same areas, then we got the formula this one. For example, if the solenoid has a different areas, this is the inner solenoid, it has the area A1 and another outer solenoid has the area A2 like this. There are two solenoids set here, then the outer solenoid has the area A2. Then if A1 is less than A2, okay, then we have to take the effective area, we have to take as inner area. Then the mutual inductance between the two coaxial solenoids which have the different areas, mutual inductance between two coaxial solenoids is that formula, one formula in terms of small n1, small n1 into mu naught into small n1 into small n2 into A1 into L we have to write, and another formula is we can write like this, that is mu naught capital N1 capital N2 A1 by L. These are the two formulas that we have to use. But here instead of using the two areas, that A1 and A2, okay, here when they give the two areas A1 and A2, if A1 is less than A2, then we have to take the less area, that is A1. Okay, right. And now everyone, you have to take the screenshot and note it. And this mutual inductance between the two coaxial solenoids is very important topic, and this derivation, it will come for the 3 marks, and either based on this problem they may ask, or as this derivation they may ask. Okay, you practice properly this derivation, and if you have any doubt you can ask me. And now I am going to rub this total, and after that I am going to explain one problem related to this mutual inductance between two coaxial solenoids. Okay. Okay, everyone listen it here. I am going to explain two problems set here. One problem is based on the concept that we already discussed. Okay, mutual inductance between the two coaxial solenoids. Right? If the coaxial solenoids have the different areas, you have to take the smaller area. The formula for the mutual inductance already you know, that is mu naught N1 N2 A. This is in terms of small n1 N2, mu naught N1 N2 A L. Okay. Or in terms of capital, then we can write as M is equal to mu naught N1 N2 A by L, where N1 N2 are the total number of turns in the first and second solenoid. N1 small n2 are the number of turns per unit length, number of turns per unit length in two solenoids. Let us see here what are the given data and then how to solve the problem. It was very simple, and listen very carefully. Okay, right, let us start. And there is two solenoids are there here. This is the first solenoid. Okay, and this is the another solenoid we will take here like this. This is another solenoid. There are two solenoids are there here. Let us see the first, a solenoid of length 50 centimeters. The one solenoid has the length 50 centimeters. It is nothing but a half meter, right? Convert into meters, that is 50 by 100, 1 by 2 meter, right? Okay. And it has the turns. We can take this as one solenoid. It has the number of turns. Okay, the first solenoid we will take. First solenoid, it has the number of turns, right? We can take as the number of turns per unit length. They gave us 20. Number of turns per centimeter. Okay, this is the per centimeter they gave. We convert into meters per meter. You have to per centimeter convert into meter by 10 power minus 2. It comes to the numerator, right? And it is a 20 power 2, 10 power 2 per meter. Okay, turns per meter. You will get turns per meter. Here turns per centimeter they give. Then when you convert turns per meter, then it will be changes like this. And one more data, some more data they gave is that what they give, area of cross section of the inner solenoid, right? What is that? 40 centimeters square, right? One solenoid 40 centimeters square. You convert that into meter square. 40 into 10 power minus 4 meters square, right? Centimeter means 10 power minus 2, square means 10 power minus 4, and it is completely surrounded by another solenoid. Okay, it is surrounded by another solenoid. Okay, then second solenoid, it is its area and everything we can write. What is it? its number of turns per unit length is again the second surrounds with the same length, the length is same. Area of cross section is again 25 centimeter square and the 20 turns per centimeter, right? Again 20 turns per centimeter. 20 turns per centimeter convert into meters, right? 20 into 10 to the power of 2 turns per meter, okay, per meter. And then after that A2 we can write A2 area of the another solenoid is 25 centimeter square. You convert this into meter square, that is 25 into 10 to the power of minus 4 meter square, right? Okay. Then here the two areas they give, they are asking to find out the mutual inductance between this system. Mutual inductance formula is what? Yes, you know, tell me, can you tell? There is one formula, that is mu naught n1 n2 into al, when you know the number of turns per unit length. Total number of turns if you know, then mu naught capital N1 capital N2 a by l also. This you substitute all values. Mu naught value is 4.10 to the power of minus 7 and n1 is 20 into 10 to the power of 2, n2 is also 20 into 10 to the power of 2. Okay, we have to change a little bit. N1 is the 20 into 10 to the power of 2, N2 is 20 into 10 to the power of 2. Here in the formula we have to take mu naught N1 N2 AL. Which area we have to take? That is the important. Okay, which area we have to take? The area, inner area we have to take. Inner area, smaller area we have to take. The smaller area is what? 25 centimeter square is the smaller area comparing with the 40 centimeter square. Then inner area we have to take, inner area is A2. If inner area is A1, then we have to take A1. Inner area is A2 means A2 we have to take, okay. When if A1 is less than A2, right? If A2 is less than A1 in this case, that's why we are taking the area as A2, okay. You should take the inner area, remember that. And A2 N1 is what? 20 into 10 to the power of 2 into A2 is also 20 into 10 to the power of 2 into A2 is what? A2 is the inner area, right? Smaller area we have to take, that is 25 into 10 to the power of minus 4 into L. L is what? 1 by 2. That's all. Now we have to simplify this. We will get answer. It was very easy, right? And you can simplify it yourself and write the answer in the comment box and what you will get the answer, right? It was very easy and you understood, I think, every point. In the just we have to concentrate one point, that is a mutual inductance formula, you know, right? In this you have to substitute all in SI system. Mu naught value is the permeability of free space N1 N2 and A2 into L. But here why we are taking A2? There are two areas are there. Inner area we have to take, smaller area we have to take when they have the different areas. And the answer you will get as like this, that is 7.85 into 10 to the power of minus 3. 7.85 into 10 to the power of minus 3 Henry is nothing but 7.85 millihenry. This is our solution, right? And you note it and carefully write in your notes. It was very easy, okay, right? Now let us go for the another problem that is given in the diagram in the board. It is given on the board. Look at here, there are two concentric coils, one of small radius R1 and other of large radius R2. There are two coils such that R1 less than R2 are placed coaxially with centers coinciding. Obtain mutual inductance of arrangement. Okay, this is again we have to derive the mutual inductance formula, but in case of not solenoids, it is in case of coaxial circular coils. It was very simple, and if you not understood the coaxial solenoids, if you listen it here again you can understood. I will explain clearly. This is the one solenoid, one coil. This coil has the number of turns. For example, this coil has the number of turns N1, okay, and this coil has the radius R1. This is the inner coil, and there is another coil, coaxial coil. This coil has the radius R2 and it has the number of turns N2, right? And R1 is very much less than R2. Then our question is that mutual inductance between these two coils we have to find out. Here the current through the outer coil is I2, right? Current through the outer coil is I2, we can consider, right? Then when the current changes in the outer coil is in the outer coil, field will generate magnetic field. What is the magnetic field at the center of the outer coil? That is magnetic field due to this is a circular coil, it carries I2 and number of turns N2, its radius is R2. Then the field generated by it is B2, that is B2 is equal to mu naught Ni by R, 2R. This is you know already, magnetic field generated by circular coil. And when the current passes through the outer coil, it can generate the field. In that field, this inner coil is there, that's why the field link with the inner coil. When the current changes in the outer coil, the flux link with the inner coil changes. Due to the change in the flux, then the inner coil current induces. This is called as mutual induction. Then our question is that they are asking to derive the formula for the mutual inductance, that is a capital M, right? And you listen very carefully, and this is very important. It's a previous CBSE question for the 3 marks. Let us see here. It was very simple. Okay. And the magnetic induction at the center of outer solenoid, right? At the center of outer circular coil. What is that? Can you tell? Outer circular coil, that is a B2, right? It is mu naught N2 I2 by 2R2. And here we know in mutual induction, flux link with the inner coil, magnetic flux link with inner coil. Magnetic flux link with inner coil, according to mutual induction we write magnetic flux link with inner coil. Yes, what we write? That is flux link with the inner coil is N151. That is depends upon the current in the outer coil. That's why we write it is proportional to I2. But when the proportional is removed, we will get one constant, that is the mutual inductance. M12 into I2 we write. Mutual inductance in the first coil due to second coil. And here we write the phi1 formula, N1 into phi1 is what? Phi1 we write as phi1 is the flux link with the inner coil, right? Okay, flux link with the inner coil depends upon the current in the outer coil. And that is a mutual induction. Flux link with the inner coil formula is flux link with the inner coil. Phi1 we write as BA cos theta, right? BA cos theta. But the thing is that we have to flux link with the inner coil. That's why area of inner coil we have to take. But the inner coil is in the field of outer coil. That's why we have to take B2. Right here we write the phi1 as B2 A1 we have to write. But the field due to outer coil is outside. And area vector is also outside, that's why we write theta as 0. Then here we will get M12 into I2, and here this is equation 1, and from equation 1 you substitute the B2 formula it here, then we will get N1 into B2 is mu naught N2 I2 by 2R2 into A1 we have to write. Okay, A1 cos 0 value is 1. And this is M12 into I2, this we are writing from equation 1. And then after that, this I2 gets cancelled. Look at here, this I2 and I2 cancel. And then after that, here we write the M12 formula. M12 formula is mu naught N1 N2 A1 by 2R2 we can write. Okay, M12 is this one, this is mu naught N1 N2 A1 by 2R2. A1 is the area of inner coil. What do we write the A1? That is write as mu naught N1 N2 pi R1 square by 2R2. This is the equation. This is the mutual inductance. From this we write one thing, that the mutual inductance is proportional to R1 square by R2. Look at here, mutual inductance proportional to R1 square by R2. Then they will ask like this. They may ask to show this one, or otherwise they may ask to derive. In this question they are asking to derive the mutual inductance formula. This is the mutual inductance formula, very simple. And if you have any doubt you can ask me, right? Mutual inductance between the due to inner coil, mutual inductance in the inner coil due to outer coil. But the mutual inductance in the outer coil due to inner coil also same, right? We will get this same formula. Okay, and this is one problem, and I will give one homework and then you can note it. Take the screenshot and note every point, and I will give the homework and do it, and you can share your answer in the comment. Okay, look here, this is your homework problem, and it was very nice problem what they gave and what you have to find out. Look at here, this is based on the mutual inductance between the two coaxial solenoids. This is the homework problem for you. The solution and right answer in the comment. Okay, do the solution and write answer in comment. Okay, right. Do it and write the solution in right answer in the comment box. What is this? A solenoid coil has 50 turns per centimeter. One solenoid has 50 turns per centimeter along its length, and area of cross section 4 into 10 power minus 4. One solenoid number of turns per unit length they gave, small n1, and area they gave. 200 turns of another wire are wound round the first solenoid. Over the first solenoid there is another wire that is wound, another solenoid. It has a total number of turns 200, and the two coils are electrically insulated from each other. The two coils are electrically insulated. Calculate the mutual inductance between the two coils given mu naught is equal to 4.10 to the power of minus 7. This is also previous problem. It's a in the CBSE previously it came, and note it and try it. And if you will not get, then you can contact me, then I will give the solution. Thank you for watching my lectures. Subscribe and share to your friends.